Hello everyone. In this video, we're going to take a look at an integration technique called partial fraction decomposition. Now, partial fraction decomposition is a procedure that we can use to evaluate the antiderivatives for rational functions. Remember, a rational function is the quotient of two polynomials. For example, like this right here, 5x minus 3 divided by x squared minus 2x minus 3. So this partial fraction decomposition technique will give us a procedure that we can follow to evaluate antiderivatives for rational functions like this. Now, the easiest way to explain this is to go through some examples, and then we'll come up with a general procedure that we can follow. So the first thing we're going to do is take a look at this example that illustrates what are called linear factors for a polynomial. So let's consider this antiderivative that we want to evaluate down here. So we want to evaluate the indefinite integral of 5x minus 3 divided by x squared minus 2x minus 3. Alright, so take notice that the denominator here, x squared minus 2x minus 3, can be written as the product of two linear factors. So it can be factored into the product of x plus 1 times x minus 3, right? You notice that? Okay. So if we want to evaluate the antiderivative of this function right here, which factoring the denominator is the same as this right here, if we could somehow take this rational function and write it as some constant divided by x plus 1 plus some other constant divided by x minus 3, then you see the integral of the right-hand side here would be very easy to evaluate, right? You notice, so if we were trying to evaluate the indefinite integral of this, it would just be the indefinite integral of this plus the indefinite integral of this, and both of these are very easy to evaluate because the first one here is just a times the natural log of x plus 1 plus, and the second one is b times the natural log of x minus 3, right? So then we could very easily obtain an answer to this problem. So the question is, can we find these constants a and b that do this for us? Okay, and also take note that when you evaluate the antiderivative of this, you're using just a little substitution, u equals x plus 1, but it's a very easy substitution, right? And you get this right here. Okay, now we do have a procedure to find those constants, a and b, and down here we have it listed. Now keep in mind this is a fairly easy example, and we'll see what happens when we run across more complicated examples in a second. So what we do, we want to find these a and b terms that will do this for us. So here's our procedure. You take your rational function, factor the denominator into linear terms. So here we have it factored as x plus 1 times x minus 3. Write this as a over x plus 1 plus b over x minus 3. Now you'll also notice one thing when we do this here. It is important that the numerator right here have a lower power than the denominator. You notice this is a polynomial of degree 1. This is a polynomial of degree 2 in the denominator. For this technique to work, the degree of the numerator must be less than the degree of the denominator. Now if it isn't, as we'll see in some examples later on, you can just use long division to reduce the power of the numerator, so it's going to be less than that of the denominator. Just do long division, and we'll take a look at that later. But here we don't have to worry about that. Okay, so what we do is we simply write it like this. Okay, right here. Now what we do is we take this right here and we just simplify it, cross multiply, right? When you want to simplify a fraction, a over b plus c over d, when you want to combine these terms, actually do the addition here, it's just going to be a times d plus b times c over b times d, right? Okay, and that's the same as finding a common denominator. And when we do that, we get a times x minus 3, see right there it is, plus b times x plus 1 right there, divided by the x plus 1 times x minus 3. Okay, so right there that is. Now, so we see then that the left-hand side is supposed to equal the right-hand side, and we see that the denominators are exactly the same, right? This is exactly the same as this over here. So that means then if we're going to have equality here, the 5x minus 3 must equal a times x minus 3 plus b times x plus 1. So we set the numerators equal to each other. And now let's see if we can solve for the a and b. Now, there are two ways you can do this. One way is once you have this equation written down here, once you set the numerators equal, you can pick strategic values for the x. For example, if I let x equal 3, you notice this will go away because 3 minus 3 is 0. And what we'll end up with is 5 times 3 minus 3 equals, that term goes away, b times 4. Okay? And then so this is going to be 12 here equals b times 4. And that implies that the b equals 3, which is what we have right here. Okay? So that's the procedure. Once you let x equaling 3, this is the procedure to follow to get the conclusion that b is equal to 3. Okay, and then you can do the same thing, but pick an x value so that this term is equal to 0. Okay, well, x equals -1. We'll do that. Okay, so letting x be -1, put -1 in here for the x's, we get 5 times -1 minus 3 equals a times -4. And then solving for the a right here, let's see, what do we get here? We get -8 equals -4 times a. And so that implies that the a is equal to 2. And that's what we have right here. Okay? And then that's it. We've really finished our problem now. We just need to do the integration. So we have found out that this is true, that 5x minus 3 over x squared minus 2x minus 3 is equal to 2 over x plus 1 plus 3 over x minus 3. And you can double check that if you do the cross multiplication here with these terms, this side, the left-hand side, will become the right-hand side. And now we can simply integrate each side, right? This side being very easy to integrate. And what we get is this down here. So here we have our indefinite integral. It's equal to the integral of this indefinite integral plus this indefinite integral. This is, of course, 2 times the ln of x plus 1. This is 3 times the ln, absolute value, x minus 3, plus c. And there you go. You have your answer. All right, so that technique is called partial fraction decomposition. Now that was a fairly easy example because the denominator factored into very nice linear terms, and also the linear terms were different from each other. Notice you had x minus 1 times x minus 3. It wasn't something like x minus 1 squared, which is what we're going to take a look at in the next example. What happens when that occurs? The procedure is going to be just a little bit different. Now let's take a look at this example. So here we want to evaluate the indefinite integral of 4x plus 1 divided by x squared plus 4x plus 4. Now, what we're going to do is we're going to look at a procedure that might seem reasonable at first based on what we just looked at, but it actually doesn't work and has a problem. And then what we're going to do is fix that problem and come up with a correct procedure to follow. So you'll notice that with this rational function, the denominator factors as x plus 2 squared. So based on what we looked at previously, it would seem reasonable that we would take our function, so we have 4x plus 1 over x plus 2 squared, right? The x plus 2 squared, that's what this factors as, and try to write it as a over x plus 2 plus b divided by x plus 2. All right, that's following a procedure similar to our first example we looked at. However, this is not going to work. We're going to have to modify this a little bit, as we'll see. Now let's see why it doesn't work first. Well, if you try to solve for the a and the b by writing it in this manner, so we would cross multiply these two fractions and simplify them. So you see we get a times x plus 2 plus b times the x plus 2 here, divided by the product of the denominators, x plus 2 squared. And now, of course, you would set 4x plus 1 equal to a times x plus 2 plus b times x plus 2. Now you'll notice if we try to solve for the a and b by picking a strategic value for x like -2, we end up with a nonsense statement. So taking this equation, you'll notice if I let x equal -2, what we get then is the left-hand side is going to be -7, right? -8 plus 1. And then the right-hand side is going to be 0. Both of these terms are going to be 0 when I put -2 in for the x. And we get this statement. Well, obviously -7 can't equal 0, right? This is nonsense. So what that tells us is that there is actually no solution to this problem. There are no constants a and b that will work to give us equality here. So there's no solution. All right, so the procedure that we had previously followed doesn't work for this example. Well, actually it does. We just need to change something a little bit. And here's what we need to do down here, you'll see. Now here's what we should have done. Instead of writing 4x plus 1 divided by x plus 2 squared as a over x plus 2 plus b over x plus 2, we should have written it as a divided by x plus 2 plus b divided by x plus 2 squared. You see, this will still work, and if we simplify it, it will give us the left-hand side. Notice if we cross multiply this, what we'll get is right, that's what we get if we cross multiply this. Now you'll notice that I can factor out an x plus 2 from the numerator, and it will cancel with one of the x plus 2 terms down here. So that is how this simplifies. And now you'll notice what we need to do is set the 4x plus 1 equal to the a times x plus 2 plus just b now. So you see, by writing it like this, the problem that we had previously was that both the a and the b had an x plus 2 term associated with them, and when we let x equal -2, both of them went to 0. Well, now we don't have that problem, you see, by writing it like this. That problem doesn't occur, because if we put -2 in here for x, only this term goes to 0, and the b will be remaining. So we won't get a ridiculous statement like -7 equals 0 now. So this is exactly what we do right here. And now you see, just picking strategic values like -2 for x, we get that b is -7. Notice if we set from right here, if I put -2 in for the x here, this goes to 0, and we get -7 equals b, right? 4 times -2 plus 1 is -7, and this term goes to 0. And now if we go back to this equation again, and we put the -7 in for that b, you'll notice that we get 4x and just pick any other value for x now to put in here. The most convenient value would be 0. So if we let x equal 0 now, you'll notice that we get 1 equals 2a minus 7. Bring the 7 over, so that implies that a equals 4. And there you go. So there are the two values that will give us this equation up here being true. So now what we have is this. So now we have the indefinite integral of 4x plus 1 divided by x plus 2 squared. Remember previously this was x squared plus 4x plus 4, and we factored it as this. So now we can write this indefinite integral as the integral of this 4 over x plus 2, that's a over x plus 2, minus 7 divided by x plus 2 squared. Now, the first integral is going to be 4 times the ln of absolute value x plus 2. And the second one here, you have to remember that the indefinite integral of 1 over u squared du is -1 over u to the first power. And so the indefinite integral here is simply going to be 7 over x plus 2. And there you go. We have our answer. So the previous two examples now give us a general procedure that we can follow when our denominator factors into linear terms, and that's what we have down here. Now here's a general rule we can follow. When you take the denominator of your rational function and factor it, for each linear factor of this form, p times x plus q, where p and q are constants, raised to the mth power, your partial fraction decomposition should include this expansion right here. So it should include the terms a sub 1 over px plus q plus the next constant a sub 2 divided by px plus q squared plus the next constant a3 over px plus q cubed, and you do that all the way up until you get to a sub m, that's the mth constant, divided by px plus q to the mth power. For example, suppose you want to find a partial fraction decomposition for this rational function. Now you notice the denominator is already factored for us, so it has a single linear factor x plus 2 cubed. So that means that our partial fraction decomposition would look like this. So you see we have a over x plus 2 to the first power plus b over x plus 2 squared plus c over x plus 2 cubed. So you notice that that is of this form up here, where the m is equal to 3 in this case. So then down here we describe how to solve for the a, b's, and c's. You would do what we had done previously in the examples. You would just take the right-hand side here and simplify it, add these fractions together by cross-multiplying or finding a common denominator. So you notice down here that's what we're doing. The first term here, we multiply the numerator and denominator by x plus 2 squared. The second term, we multiply numerator and denominator by x plus 2. And the third term, we don't need to do anything. So that way, each term has a x plus 2 cubed in the denominator. Add everything up, and this is what you would end up with. And now at this point, you would set the numerators equal to each other. 4x plus 1 would be set equal to this. And then you just need to solve for the a, the b, and the c by picking 3 different values for x. And you can pick a strategic value in this case, one where some of these will go to 0. Let's just move down here a little bit. So you notice if we have this where we set the numerators equal to each other, if we set x equal to -2, these two terms just go to 0, and we end up with c equaling -7. So then at that point, we can pick 2 other values for x like 0 and 1. And, well, let's just note one thing. After you know that the c is equal to -7, you would have this equation. And now you need to solve for the a and the b. And so what you can do is pick any other 2 values for x, like easy values 0 and 1, most convenient ones to pick. You just have to pick something different than -2. When you pick x equaling 0, you get this equation. When you pick x equal to 1, you get this equation, just by putting the x in over here and simplifying. And now you have 2 equations and 2 unknowns right here. You can solve those 2 equations using substitution or the elimination method if you're comfortable with that. And then you can solve for the a and the b. So solving those for a and b, you'll find that a is 7/6 and b is -11/6. And then you would have your partial fraction decomposition completed down here. Now let's take a look at an example where we evaluate an antiderivative. So here we want to evaluate this indefinite integral. Now first of all, notice that the degree of the top is less than the degree of the denominator. So that's good. We don't have to do any long division. So what we want to do is factor the denominator. And you'll notice that if we pull out an x from here, we get this. And then this quadratic right here factors as x plus 1 squared. Okay, so then what we have is our integrand right here can be written like this, where the denominator is now factored. Okay, so the denominator has 2 different linear factors. It has x and x plus 1 squared. For the x, that's just x to the first power, so all we need is a over x. For the x plus 1 squared, we're going to need b over x plus 1 plus c over x plus 1 squared. Okay, and so now what we need to do here is solve for the a, the b, and the c by adding these fractions together and then setting the numerators equal to each other. So down here we do that. Notice that We can either cross multiply or just find a common denominator here. Now if we were to perform cross multiplication here, we'd multiply the a by these two terms, and that's what we have right here. Then we'd multiply the b by these two terms, this one, and that's what we have right here. And then we'd multiply the c by these two terms, and that's what we have right here. And then we'd divide by the product of these three terms, and you would get this. Now notice at this point you can do some simplification. Each of these terms has an x plus 1 in it. You can factor it out and cancel with this x plus 1 right there. So this one will cancel with that one of these will cancel, and one of these will cancel, and you end up with this right here. So it doesn't matter whether you use cross multiplication or just finding a common denominator, whichever way you would like to do it. Now at this point we can set the numerators equal, so we would set this right here equal to 5x plus 8 plus 1, and that's what we have right here. And now we just want to pick strategic values for x and solve for the a, the b, and the c. All right, so that's what we're doing down here now. So you notice, looking at the right-hand side here, if we pick x equal to 0, these two terms will go away, be eliminated, and we can easily solve for the a. So letting x equal 0, if I put 0 in for the x's here, I get that on the left-hand side here, 1 equals a, and okay, there you go. So a is 1, so we know that. So we can put a 1 right there. Then if we let x equal -1, you notice that these two terms will cancel, and then you'll be able to solve for the c. So if we put -1 in for the x here and over here, then we will get that negative c equals 5 minus 8 plus 1, or c equals 2. All right, so now we have the a and the c. Now, we have this so far. We figured out what the a and c are. We don't really have any other strategic values to pick for x. Any values where if we put it in for the x's, some terms are going to cancel. So at this point, we just have to pick any value for x other than 0 and -1. So let's pick x equaling 1, in which case putting 1 into this equation right here, we can then solve for b. So if we let x equal 1, that will give us this equation right here. And simply solving that for b, that will give you that b equals 4. You can just easily verify that. That's just simple algebra there. And so now we have our partial fraction decomposition complete. And so what we can write is this. So our integral of what we wanted here is equal to, remember what you have in here is going to be 1 over x, that's a over x, plus b over x plus 1, plus c over x plus 1 squared, and you can simply break the integral up like these with these three different integrals here now. First one is going to be the ln of x. Second one is going to be 4 times the ln, absolute value, x plus 1. And this one right here is -2 over x plus 1. Remember, once again, the integral of 1 over u squared du is -1 over u. So that's how we get -2 over x plus 1 to the 1 power, like that. And then there's your answer. And that's it. Okay, so you see how we had to tackle this problem. Now in this part of our lesson, we're going to take a look at what happens when you have irreducible quadratic factors in the expansion of the denominator of your rational function. Now, what we mean by an irreducible quadratic factor is this. Consider this polynomial right here. Okay, so this is a big long polynomial here, x to the 5th power plus 9x to the 4th and so on. Now, that factors like this. Now, you don't have to do that. I'm just telling you that this is how it factors. So you notice we have these linear terms, x plus 1 times x plus 3 squared. Then we have this quadratic term here, x squared plus 2x plus 5. Now, this term right here, or this quadratic, does not factor over the real numbers. You cannot write this as x plus a times x plus b. You cannot expand it like this. And the reason you can't do that is because if you set this equal to 0 and try to find the roots, so if you take that, right, and you set it equal to 0, using the quadratic formula, you would get that x equals negative b plus and minus the square root b squared, so that would be 4, minus 4 times 1 times 5, minus 4ac, remember, so that would be minus 20, over 2 times a, or just 2. So you notice that what you get here is, alright, so what you have here is the square root of a negative number. So this does not factor over the real numbers. Now it does factor over the complex numbers, but we're not going to go into the complex numbers in this course. So there's nothing else that you can do with this. It just has to stay here. So how do we handle the partial fraction decomposition? Well, let's take a look at this next example. So here we want to evaluate the indefinite integral of this rational function. Now, the denominator we already have factored as a linear term times an irreducible quadratic term. You can verify that this is irreducible if you try to set this equal to 0 and apply the quadratic formula. You would find that you get and so you see this is b squared minus 4ac underneath the square root, and of course that is a negative number. So these would turn out to be complex roots. So this does not factor over the real numbers. So how are we going to do this problem? What are we going to pick for our partial fraction decomposition? Well, we have that right down here. Oh, and notice one other thing before we look at this. Notice that the degree of the numerator is less than the degree of the denominator, right? The degree of the denominator is 3 in this case. If it were not, we would have to do long division first. And we'll look at an example like that next. Now here is how we're going to do our partial fraction decomposition right here. So the linear term, we have our a over x minus 2, right? Just like we did before. Now for the quadratic, right here, what we're going to write is bx plus c divided by the irreducible quadratic. So that's what you do when you have an irreducible quadratic as a factor of the denominator. You add in a term like this. Now what we have to do is solve for the a, the b, and the c, and then once we get them, well, then we will be able to integrate this by integrating each of these terms. Now this one's going to be easy to integrate. This one's going to be a little more involved, however. What we're going to have to do is complete the square on the denominator, and you'll see how that works out. But you will be able to do this. Now, to solve for the a, the b, and the c, what you have to do is simplify this by adding, and that's what we have right here. So, we just do cross multiplication or finding a common denominator. A times this term plus bx plus c times the x minus 2, that's what we have right here in the numerator, divided by x minus 2 times x squared minus 2x plus 15 right here. And there you go. Now what we have to do is set the numerator here equal to the x squared plus 1. All right, so that's what we have right down here. Okay, now we're going to take this equation here and solve for the a, the b, and the c. Now you notice we can pick some strategic values for x right here to try to solve for the a, b's, and c's. Notice if we pick x equaling 2, that this term will go away and we'll easily be able to solve for the a, right? So you have to look for those values that you can pick to make your life a little easier. So letting x equal 2, so this goes away, and then what you end up with right here, of course, is 5 equals, and when you put 2 in here, you're going to end up with 15. Notice that if you put 2 in here, you get 4 minus 4. Okay, so they cancel, you just get 15. So you get a times 15. So a is going to be 1/3 right there. Okay, so now that we have the a, now we can attempt to solve for the b and the c's. So let's go down here a little further. So here we put the 1/3 in place of the a, and we still have to solve for our b and c. So let's see, you have to think about, well, what good value could I pick for x to try to make my life a little bit easier? Well, you notice if we put 0 in for x, this b term will drop out, and then we'll have c alone in this equation, and we can solve for the c. So that sounds good. Let's put 0 in for the x, and that's what we do. When we put 0 in here for x, what you're going to get is, on the left-hand side, you're going to get 1 equals, and right in here, we're going to get 1/3 times 15, so that's 5, plus, that's going to go to 0, and you're going to get c times -2. And then solving that for c, just take the 5 over, you get -4 equals -2c, and so that implies that c equals 2, so that's what we have right here. All right, so now we have this equation down here, and now what you can do is just pick any other number to plug in here for x. It doesn't matter what you pick. It just can't be 0 or 2 because you already used those. So just pick any other convenient number like 1, put 1 in here for the x's, right, and then solve for the b, and you will get b is 2/3. Just to verify this quickly, if you put 1 in here for the x's, what you're going to get is, and let's see right here, if we put 1 in for these x's right here, we're going to get 14. This would be -1. All right, so that's what you would get. And then just taking this over to the other side, dividing by -1, subtracting 2, you can verify that you are going to get 2/3. So now we have determined this. Here's our partial fraction decomposition. So for the integrand right here that we were looking at, we have determined that it can be written like this. Okay. Now what we need to do is integrate the right-hand side. So the integral of this piece, that's going to be easy. The integral of this one is going to be a little bit more difficult. So let's see how we do that. Now down here we have our two integrals set up that we have to evaluate. So we have this one, the first one, right here. Now that's easy. 1/3 natural log absolute value x minus 2. No problem. Now this one right here, what we're going to have to do is complete the square on the denominator. Okay, now if you complete the square, you're going to get this down here. X minus 1 squared plus 14. Just to verify that quickly, you know, when you complete the square, you take the -2, divide it by 2, and square it, add it in, subtract it back out. So you're going to have, and remember, you know, what you're going to put in here is b over 2 squared. In this case, the b is -2, so squaring that, that's going to be 1. Subtract it back out so you don't change anything. And you see what you get here now. This is going to be x minus 1 squared plus, and what's remaining here is 14. All right, so that's what we have. So you see we completed the square on that. Now what we're going to do is a substitution. Let u equal the x minus 1, because we would like this to be in the form 1 over u squared plus 14, because the integral of this we identify as an arctangent problem that we've seen before. So we let u equal x minus 1. That's what we have right here. The du is going to be dx, so nothing changes. We don't introduce any constants because of that. Now you will notice also that we're going to have to go back to this equation and write x as u plus 1. So in for this x right here, we substitute u plus 1. Okay, so that's right here. X minus 1 becomes u, and the dx right here is just du. No constants introduced because of this. And so this is what we have now, right here. Now this part right here, this integral, what we can do is simplify the numerator and split it apart. You'll notice that the numerator, that can be written as 2/3 u plus, and then 2/3 times 1 plus 2, that's going to be 8/3. And then we have that divided by the u squared plus 14. Now simply split this fraction apart, you know, write it as 2/3 u divided by this. That's what we have right here. And then plus 8/3 divided by u squared plus 14. That's what we have right here. So you notice how we split that apart. Now, each of these integrals can be evaluated. This one right here, the first one, is going to be another substitution, right? If I let v equal u squared plus 14, right here, you see that's what we have. The dv is going to be 2u du. And so this integral right here is going to become 1/3 the natural log absolute value u squared plus 14. Let me just elaborate on that a little bit here. You notice if we do this substitution down here with the dv equaling 2u du, what this is going to become is 2/3 integral u du is going to become dv over 2. And then the u squared plus 14, that's just going to be our v. And you see what we get here is that 2 and this 2 cancel, and we end up with 1/3 integral dv over v. Okay, so that's how we get the natural log of v, and v is u squared plus 14. So right there's the v. Okay, so that's how we handle the first one, right? And then the second one, this one right here, is an arctangent problem with a squared equaling 14. So that means that a equals the square root of 14. So this integral right here is going to be 1 over root 14 times the arctangent of u over root 14, right? And so that's what we have right here. And then we have the 8/3 also. So you see 8/3 times all of that. So right there, that's the integral part that I have circled right here. You have your constant of integration also. All right, so now we have our answer down here, except the only thing is we need to go back to the x's. So we need to go back through our substitutions. Let's see, what did we let u equal here? You see I've got all these u's in here. So the u was x minus 1. Just put that back in place of the u's here, and we get our answer. So finally down here you see our answer right there, and that's it. Okay, so that's what we had to do in this case. Now here we have a rule for when you have irreducible quadratics in the factorization of the denominator of your rational function that you want to integrate. So for each irreducible quadratic that you have of this form, so the ax squared plus bx plus c would be an irreducible quadratic, so it cannot be factored over the real numbers, and it is raised to the mth power. So when this factor occurs in the factorization of the denominator of your rational function, then you should include these terms in your partial fraction decomposition. So you notice that we have a1x plus b1, where the a1 and b1 are just constants, divided by your quadratic to the first power. And then we have plus a2x plus b2, a2 and b2 are constants, divided by your irreducible quadratic squared. And then the next term would be an a3x plus b3 divided by the irreducible quadratic cubed, and we continue all the way up until we get to a sub m times x plus b sub m, the a and b are constants, divided by your irreducible quadratic to the mth power. Now let's take a look at this example to see how this works. Suppose you want to find a partial fraction decomposition for this rational function that we have here. So you notice the denominator has a linear factor, x minus 2, and it is squared. And then you have an irreducible quadratic to the third power. Now, you can just verify that x squared minus 2x plus 15 is irreducible. If you look at the discriminant, b squared minus 4ac, you will see that this is negative. This is the term that's underneath the square root if you were to try to apply the quadratic formula. In this case, the b is negative 2, so you would get that this is 4 minus 4 times 1 times 15 is 60. And yes, that is negative, so this is an irreducible quadratic. Now in this case then, your partial fraction decomposition would look like this down here. So notice that we have a over x minus 2. That's coming from the linear term. Now we have x minus 2 squared, so we have to include another term, b over x minus 2 squared. So these two terms come from the x minus 2 squared. And then these three terms come from the x squared minus 2x plus 15 cubed. So you notice we have a cx plus d over our quadratic plus ex plus f over the quadratic squared plus gx plus h over the irreducible quadratic cubed. And so this is what your partial fraction decomposition would look like. You would then have to solve for the a, b, c, d, e, f, g, and h by simplifying the right-hand side, finding common denominators, adding everything together, and then you would set the numerator equal to the x squared plus 1, and then you would have to solve for the a, b, c, d, e, f, g, and h terms. So this would be a very involved problem. Now let's take a look at one more rule. Now here's a rule concerning long division. In order to perform partial fraction decomposition on a rational function, px over q of x, where the p and q are polynomials, the degree of the numerator must be less than the degree of the denominator. If it isn't, then you need to perform long division first. So for example, consider this problem. Suppose we want to evaluate the indefinite integral of x cubed divided by x squared minus 2x minus 3. So you notice the degree of the top is 3 and the degree of the denominator is 2. So degree of the numerator is larger than the degree of the denominator. So what you need to do first then is to perform long division. So if you do long division, you'll find that you get this expression right here on the right hand side. So you'll find that your integrand is equal to x plus 2 plus 7x plus 6 divided by x squared minus 2x minus 3. And you see, now if you want to integrate each side, this is easy. And this part right here, we can do partial fraction decomposition on to find the integral for this. Now let's just note here. Let's just do this long division quickly just to make sure you see how we get this down here. So if we divide x cubed by x squared minus 2x plus 3, just doing long division here, you'll notice we need to multiply this by an x, so we'll get the x cubes canceling. So the x cubes cancel, we get 0 x squared minus negative 2x squared, so we get 2x squared. 0 x's minus negative 3x, and no constant terms. And then we can multiply this by a 2 to drop out the 2x squared here. So the 2x squares drop out. 3x minus negative 4x is 7x. 0 minus negative 6. And there you go. And so you see how we get this right here. So this long division tells us that x cubed divided by x squared minus 2x minus 3 is equal to x plus 2 plus the remainder divided by x squared minus 2x minus 3. Okay, so that's how we get this term right here. Now, what we want to do is integrate each side, of course. This is easy. That's just going to be x squared over 2 plus 2x. Now, this integral right here, we're going to have to perform partial fraction decomposition. Now notice that x squared minus 2x minus 3 factors as x plus 1 times x minus 3. All right, you can just easily factor that, and that's what you'll get. So we want to write this as a over x plus 1 plus b over x minus 3. Okay, so we have to solve for the a and b, and we do that by simplifying this, and then we get this right here by finding a common denominator or just cross multiplying. And then we need to set the numerator here equal to this numerator over here, and then just pick strategic values for x. So what we have is that down here. Setting x equaling 3, this term will drop out, and we obtain b equals 27 over 4. All right, if you put 3 in here for x, just verify that you get b times 4 equals, and putting 3 in right here, you get 21 plus 6, so that's 27. So that's how you get b is 27 over 4. And then putting negative 1 in for x, this term will drop out, and you'll get a times negative 4 equals negative 1. So you'll get, and so a is 1/4. So there you go. We now have then that the integral of what we originally wanted to evaluate is equal to the integral of x plus 2 plus the integral of 1/4 over x plus 1 plus the integral of 27 over 4 divided by x minus 3. Integrating each of these, this of course is x squared over 2 plus 2x plus, and then this is going to be 1/4 the natural log absolute value x plus 1, and this is going to be 27 over 4 times the natural log of the absolute value of x minus 3 plus c, and there is your answer. So now you see how to do a problem like this when the degree of the numerator is larger than the degree of the denominator. You just have to perform long division until you knock down the power of the numerator and then apply the partial fraction technique. And that concludes this video about how to integrate rational functions using partial fraction decomposition.